All right, welcome back everyone. Today we are going to go ahead and cover mesh analysis. Okay, so goals for today's class. By the end of this video, first you should be able to apply Kirchoff's voltage law and Ohm's law to determine mesh equations. We'll learn about how we can use these mesh equations and mesh analysis to analyze circuits. And finally, we'll talk about when we would want to use node analysis versus mesh analysis when analyzing different kinds of circuits. Let's start with the review question from last time. So in this review question, we are being asked to use node analysis to find the voltage V1 at node 1. So here's node 1. And we are also asked to find the currents through each resistor. I'd encourage you to pause this video and see if you remember node analysis from last time. Then we'll go ahead and do it together. Okay, so let's go ahead and try this question. So we are being asked to use node analysis. And you might recall the steps of node analysis. First, we want to identify our nodes. Then we need to choose a reference node or a ground. And we set that reference to 0 volts. Once we do that, then we apply Kirchoff's current law to each node other than the reference. And then we rewrite the Kirchoff's current law equations in terms of our node voltages. And finally, in our last step, we solve the system of equations to determine our node voltages. So let's go ahead and give this a try. So in our particular circuit shown here, we are already given node 1 at this location. Notice that we also technically have nodes over here on each corner, right? I'll just call it node 2, node 3. Then we also have a node down below. And notice this one was already grounded. Notice we're given this ground sign, so we will use this node as our reference. So we assign this node a voltage of 0 volts. If you're not already told which node to use as a ground, it's a good practice to use one that's connected to a lot of things. That way you can set a lot of things equal to 0. Okay, so we've identified our nodes, and we've chosen our reference node. Let's go ahead and apply Kirchoff's current law to each node in our circuit. In this case, let's focus on node 1 because that is the node that we are trying to find voltage of. If we need, we can write node equations for the second and third node, but we definitely need to solve an equation at node 1. So let's apply Kirchhoff's current law to node 1. And in this case, I'm going to assume some currents. So I'm going to assume that current I1, assume I1 flows from the 12-volt source to node 1. What about this current, I2? Do we know what I2 is? Notice current, we don't even need to assume. We know I2 must be 25 milliamps, or 0.025 amperes, right? So that I2 is given to us. And then I'm going to let I3 be my current from node 1 to the ground through the center path. So notice I have I1 and I2 entering, I3 leaving. So by Kirchhoff's current law, I give current entering a positive sign, current leaving a negative sign. I end up with plus I1 plus I2 minus I3 equals 0. That is my Kirchhoff's current law equation for step 3. Notice how much it helps to draw pictures here. Don't be afraid to draw pictures if it helps you keep everything straight as you work on these circuits. Okay, so let's continue with our process. We have our Kirchhoff's current law equation. So remember, we determined that we had plus I1 plus I2 minus I3 equals 0. We have this. Our next step is to rewrite that equation in terms of my node voltages. Let's go ahead and do that. Notice that we know that current I2 is just 25 milliamps, or 0.025 amps. So we already know what I2 is. We just need to write expressions for I1 and I3 in terms of V1 and the resistances. Let's first consider I1. Well, we know I1 is flowing from the 12-volt source into node 1. Node 1 is sitting at voltage V1. So in this case, we can write our current I1 using Ohm's law. we know that the voltage we see in current I1 is going to be equal to the voltage across that 100 ohm resistor, and it's going to be equal to 12 minus V1, because I start at 12 volts. My current is flowing into V1, so I must be losing 12 minus V1 volts across that 100 ohm resistor. I also know my resistance is 100 ohms. Therefore, my current I1 must be equal to 12 minus V1 divided by 100 ohms. Notice you need to keep your units in volts, ohms, and amperes here in order to avoid unit conversion errors. Remember, I2 we already know, so we don't need to worry about I2. Now let's consider I3. We're going through a 100 ohm resistor. We're starting at voltage V1, ending at our ground, which was 0 volts. So we can draw that same picture where initially we're sitting at voltage V1, we end at 0 volts, and we pass through that 100 ohm resistor. So in this case, our voltage drop is V1 minus 0. So therefore, our current I3 must be equal to V1 volts divided by the resistance we pass through, which is 100 ohms. So now we can substitute I1 and I3 into our Kirchoff's current law equation. And if we substitute, we end up getting our node equation for node V1. So once again, we substitute, so we have plus I1, so that will be plus 12 minus V1 over 100, plus I2. Remember, I2 is 25 milliamps. Remember, we want to keep our units in terms of volts, ohms, and amps. And then finally, minus I3. I3 is minus V1 over 100. So all of this leads us to our node equation. Notice here we have one equation and one unknown. We can solve for V1. So if we just multiply both sides by 100, we end up getting 12 minus V1 plus 2.5 minus V1 equals 0. We combine terms, we get 14.5 minus 2V1 equals 0. We determine that V1 is equal to 14.5 divided by 2, which is equal to 7.25 volts. Notice once we know V1, we can plug V1 into I1 and I3 to get our currents. So we can determine here that I1 must be equal to 12 minus 7.25 over 100, and that gives us 0.0475 amps. And similarly, I3 is equal to V1 over 100, in this case 0.0725 amperes. So we have successfully found our voltage V1 and the currents through each resistor. Please make sure you understand this node analysis very clearly. This is an extremely important skill that we're going to be using throughout this course. And if you have any questions on this example, please do feel free to reach out. Okay, so real quick, let's just finish reviewing the topics from last time, and then we'll move on to mesh analysis. So once again, we learned, as we saw in our example, that node analysis uses Kirchoff's current law and Ohm's laws to write equations for each node. Specifically, we are writing equations for each node in terms of node voltages. So once we have those node equations, all we need to do is solve that system of equations for our unknown node values. As we saw in our example, it's a good idea to follow these main steps. Remember, for the purpose of homework assignments, you can use solvers such as Wolfram Alpha or MATLAB. Also, Kramer's rule will work. So again, just make sure that you have a tool available for solving those equations. If I were to ask a question about node equations on an exam, generally I would either ask you to write the equations or they would be simple enough that they could be solved by hand in a reasonable amount of time. Okay, we also briefly covered special cases of node analysis. So you saw that if we have a voltage source between a node and the ground, here we know that our voltage VB must be equal to our source voltage. You also may have noticed that I used that same technique in our example. We're down here, we're sitting at 0 volts, so I knew that my voltage right here is 12 volts. So if you see a voltage source between a node and the ground, it's actually very easy. You've got free information there. The next special case of node analysis is called the supernode. Remember, if we have a voltage source between two nodes, then we create what's called a supernode. And how you can solve this with node analysis is you apply Kirchoff's current law to the whole supernode. So in this case, we could assume we have I1 entering, I2 and I3 leaving, and we could apply Kirchoff's current law to determine that plus I1 minus I2 minus I3 is 0. And notice I can write I2 as VA over R1, I3 as VB over R2. From the supernode, I can also determine a second equation that VA minus V1 equals VB. Again, that's because VA is sitting V1 volts higher than VB. So notice, if I use these two equations, I would be able to proceed with node analysis like normal. If I knew what those current sources, voltage sources, and resistors were, I would be able to solve for VA and VB. So if you see a supernode, you should be happy because that also gives you a very big hint about how you could approach that node analysis question. One more special case. What about when circuits have dependent sources? Once again, you should be happy if you see a dependent source because you're getting free information and a hint. all you need to do is make sure you relate that dependent source to the node voltages. Then you can do node analysis like normal. Let's look at one more practice that might be similar to a homework question. We're first being asked to determine V2, asked about special cases, and then how would we determine power supplied by dependent source. Well, notice V2 is this node up here, which this whole area is actually equal to V2 volts. Right? That whole area is connected by a short, so this whole area is sitting at V2 volts. We know that we're sitting at 0 volts down below, so what would V2 be equal to? If I were to walk from my 0 volts up to V2 voltage, notice I would gain Vs volts. So in this case, V2 is equal to Vs. Next part, does this circuit contain any special cases of node analysis? Take a moment and think about it. Well, here's one special case. As we just saw, we have Vs between V2 and the ground. What about this? We've got a dependent voltage source between two nodes. So our dependent source can be treated as a supernode. Okay, so our next question. How could we determine V1 and V3? Think about that for a moment. Well, what should we do with supernodes? Notice if this whole thing is a supernode, we can apply Kirchoff's current law to our supernode. Let's briefly talk through that. Suppose we assumed that we had I1, I2, I3, and IA currents exiting our supernode. For part C, we could write Kirchoff's current law equation for the supernode. In this case, all of my currents are exiting. That's okay. Remember, I had to assume a direction. So it's okay to write it like this. We will probably end up finding that some of these currents are flowing the opposite way. And so we can correct for that later. What else could we do? Well, notice we know what V1 and V3 are. So we can actually write node equations. So we can rewrite that Kirchhoff's current law equation in terms of node voltages. For example, minus I1 would become minus V1 minus V2, or in this case, V2 is equal to Vs, right? Divided by R1. So notice if I'm plugging it in to Kirchhoff's current law, I get that. I2, notice that's V1 minus 0 volts divided by R3. Then we have current I3, well that is just V3 minus 0 over R4. And then finally we have V3 minus V2, or minus IA. Let's call V2 Vs here just to be consistent. So notice this equation is in terms of V1, V3, and Vs, right? Vs is known, or could be known. We need one more equation for V1 and V3. Notice we can also say that V1 and V3 are 8IA apart. And we know what IA is, and we can write IA in terms of V3 and Vs. So we will actually end up with 2 equations and 2 unknowns. So we write a second equation for the V1 and V3 using the supernode. Once you have 2 equations, 2 unknowns, you can solve for V1 and V3. Finally, last part of the question is asking, how would we determine power supplied by the dependent source? Well, we know that P equals IV. So we know that in this case, V is equal to 8IA, so that's nice. But what is I here? Well, notice that farther downstream of the power source, we have I1 exiting. So we know downstream at point V1, we can determine using Kirchoff's current law to find the current supplied, or the current flowing through. So I'd highly encourage you to go back through this example yourself, and this is a really good practice to make sure you understand Kirchhoff's laws. All right, so if you have any other questions about node analysis, please do feel free to let me know, reach out. And now we'll go ahead and continue on to mesh analysis. Today we're going to go ahead and cover mesh analysis. You'll see that it's very similar to node analysis, except we're using Kirchhoff's voltage law to write equations for current. Just like how in node analysis we used Kirchhoff's current law to write node equations for voltage. So, kind of similar strategy here again today. So, before we dive straight into mesh analysis, let's review some important tools that we're going to need. Okay, so let's first review Kirchhoff's voltage law. So in this review question, we're asked to write an equation for the algebraic sum of the voltages in loop number 1. So algebraic sum of voltages. Remember, we need to use a consistent sign convention. So we need to use a consistent sign convention when finding the algebraic sum. So remember, if you like to follow the bank account conventions that I like, I treat walking from negative to positive in the source to be a voltage gain. if I am going across a resistor in the same direction as my current, then I will treat this as a voltage drop because I am losing volts. And if I happen to be traveling in the opposite direction as current and I want to go the other way, then I will treat that as a voltage rise. So the important thing here is to be consistent. So if you learned the opposite convention as this, that's okay. Just make sure you follow a consistent sign convention when determining that algebraic sum. So my recommended strategy here is to walk along the circuit so I like calling it walk around the loop or around the circuit of interest. And if you know the direction of current, it's generally preferable to walk in the same direction as the current if you know that direction. Otherwise, just take a guess. So if you don't know the direction of the current, that's okay. Just assume a direction and stay consistent. So I'm going to go ahead and start walking from the lower right corner, and I'm going to walk clockwise around the circuit. Okay, so I'm going to go ahead and start in the lower left, and I'm going to walk clockwise around. So first, I go across that 10-volt source, starting at the minus end, ending at positive. So here I'm going to treat this as a 10-volt gain. So my Kirchoff's voltage law equation starts out with a plus 10 volts. Next, I'm going to walk across this 5 ohm resistor. I'm going in the same direction of my current, so I know that I'm going to start at a higher voltage, end at a lower voltage. I'm not sure how much current is flowing through there just yet, so I'm just going to write this as minus V 5 ohms. There's going to be some voltage drop across that 5 ohm resistor. Then I walk across my 9-volt source, but notice I'm starting at the higher voltage, ending at the lower voltage. By my convention, that's going to be a minus 9-volt drop. Similarly, for my 10 ohm resistor, the current is entering. I'm assuming the current is still entering because I'm walking in the direction of I1. So I'm going to treat this as a voltage drop V 10 ohms across that 10 ohm resistor. Here's my Kirchoff's voltage law equation. So again, the units here are volts. And you see that the sum of the voltage rises and drops must equal 0. If I were to ask you to write an equation like this on an exam, this is what I would be looking for. And notice, at this point, it's not necessary yet to simplify that equation. Okay, so our next question asks to rewrite the equation from question 1 in terms of our mesh currents and the resistors. In this case, we have, remember we had the equation plus 10 volts minus V 5 ohms minus 9 volts minus voltage drop across 10 ohm resistor. We have this equation. So we need to rewrite that term V 5 ohms and V 10 ohms in terms of mesh currents, so I1 and I2, and the resistors. Let's take a look at the voltage across our 5 ohm resistor. Well, we know that we have current I1 going through there. So do we know what this voltage is? Do we know what the voltage V 5 ohms is if we got a 5 ohm resistor with I1 current going through? Yeah, we got to use Ohm's law, right? Notice we can write the voltage drop across our 5 ohm resistor as our current I1 times the resistance, which is 5 ohms, right? I'll go ahead and leave it as 5I1 in this case. So remember that you want to keep your units in terms of volts, ohms, and amps. How about the voltage across our 10 ohm resistor? How much current is going through that 10 ohm resistor? Well, let's take a moment and take a closer look at this resistor. Because we know we have current I1 entering from the top, and we have current I2 exiting around in the clockwise direction, and we have that 10 ohm resistor, right? So we want to make sure we use the correct current I that's flowing through that 10 ohm resistor. But notice by Kirchoff's current law, we need to be careful that we solve for current I correctly. By Kirchoff's current law, we can write that plus I1 minus I2 minus I equals 0. Right? Because notice I1 is entering this top node, I2 is leaving, and also our unknown current I is leaving that point above our 10 ohm resistor. So we can say the current I through the 10 ohm resistor must be equal to I1 minus I2. Another way of viewing this is to think about what is the net current going through that 10 ohm resistor. If I'm standing on a boat and I want to go downward in the direction I was walking, notice I have current I1 pushing me, but current I2 opposing my boat. So notice I1 pushes me in the direction I want, I2 is a headwind or pushing against my direction. So the net current would similarly be I1 minus I2. Okay, so by this reasoning, we can use Ohm's law again. And notice that the voltage drop across our 10 ohm resistor, it's not going to be 10I1 or 10I2. It's actually going to be the 10 ohms times the net current going through there, which is I1 minus I2. Or 10 times I1 minus I2, like this. So notice, very important that you properly calculate those currents. Now we can go ahead and rewrite this equation. And so our Kirchhoff's voltage law in terms of the mesh currents Well, that equation simply becomes plus 10 volts, right? Minus voltage across our 5 ohm resistor, which was 5I1, minus 9 volts, minus voltage across our 10 ohm resistor, which was 10 times I1 minus I2 equals 0. And there you have it. There is our Kirchhoff's voltage law equation in terms of the mesh currents I1 and I2 and our resistors. All right, so look what we're doing now. In quick review question 3, we're going to do the same exact procedure, except now we are going to do that procedure on loop number 2. So let's go ahead and give this a try. So first I need to apply Kirchhoff's voltage law. So I'm going to walk, in this case, in the same direction as current I2. So I'm going to go ahead and walk clockwise around the circuit in the direction of current I2. So what do I see? Well, first I have a voltage drop across the 10 ohm resistor, so I give that a negative sign. Next, I walk across that 9-volt source. This time I'm starting at negative, ending at positive, so I am treating this as a 9-volt gain. I'm walking across a 5 ohm resistor in the same direction as my current, so I'm going to have a voltage drop. And notice I also have a voltage drop across that 1-volt source, because I'm going from positive to the negative side. And I have another voltage drop across the 5 ohm resistor at the end of my circuit. So this is our Kirchhoff's voltage law equation. So that was our quick review question 1. So now, repeating quick review question 2, now we need to rewrite the Kirchhoff's voltage law equation in terms of my mesh currents. That's I1 and I2. And the resistances. So first we have the voltage across our 10 ohm resistor. Notice once again for that 10 ohm resistor, this time I am trying to walk from bottom to top. Right? I'm trying to walk starting at the bottom, heading upward. So in this case, I have current I2 pushing me upward. I have current I1 pushing me downward. Another way of writing this is to assume I have some current I10 ohms exiting my node, but I have I2 entering my node, I1 leaving my node. So basically, by performing this analysis, we can determine that the current across our 10 ohm resistor, that must be equal to I2 minus I1. Both current I2 and I1 can flow through that 10 ohm resistor, so it's very important that we correctly capture that in our equation. So the voltage across a 10 ohm resistor, that becomes 10 ohms times our current, which was I2 in the direction we want, minus I1 opposing us. we need to find the voltage across that 5 ohm resistor next. So the top 5 ohm resistor, well, that one only has current I2 going through it. Notice current I1 is not passing through that part of the circuit, so we just give it 5I2. And similarly, the second 5 ohm resistor also has current I2 flowing through it, so its voltage becomes 5 ohms times current I2, or 5I2. So if we substitute back in, we determine our mesh equation for loop 2. We determine that we have minus V10 ohms, so that's minus 10 times I2 minus I1, plus 9 volts, minus 5I2, minus 1, minus V5 ohms, which is another minus 5I2. All that equals 0. So if I were to ask you to write a mesh equation for the current around a certain loop, this is what I'd be looking for. I'd be looking that you applied Kirchoff's voltage law and then rewrote that equation in terms of current and resistance. So, as we mentioned before, mesh analysis is very similar to node analysis, except we are applying Kirchoff's voltage law around the loop, and then we are writing equations in terms of mesh currents. So we write what's called mesh equations. Mesh analysis gives us a system of equations for current. So let's go ahead and walk through the steps of mesh analysis. So here's the general procedure you want to follow. Once again, we're using Kirchhoff's voltage law to write systems of equations for current. So first step is to identify the meshes or loops where current is flowing. We assign a current to each mesh, and if needed, assume a direction for each current. Sometimes the mesh currents will already be given to you. Other times you'll need to assume them. Once you've decided on those currents, you'll apply Kirchhoff's voltage law around each loop, just like what we did in the examples earlier. Finally, you'll solve the resulting system of equations to determine the unknown currents. Let's go ahead and do an example. So suppose we have this mesh equation here. So we have a circuit, and it might be similar to one on the homework. And we want to use Kirchhoff's voltage law to write the mesh equation for mesh 1. We want to write an equation in terms of the currents given voltage and resistances. Let's go ahead and give this a try. So let's just briefly remind ourselves of the steps of mesh analysis. So remember, first, we want to identify all our meshes and assign a current to each one. So in this case, we are already given I1 and I2, so this is done. If you were not given those currents I1 and I2, you could assume that you had two currents flowing in these areas, and you could assume a direction for those currents. You'll see that even if you happen to assume the opposite direction as I did, you would still end up getting the same result if you followed a consistent sign convention. Next step is to apply Kirchoff's voltage law, and then write that equation in terms of currents. So we write our Kirchoff's voltage law equation and then rewrite Kirchoff's voltage law in terms of the mesh currents. And then finally, we would solve the equations for the unknown currents. So here we just care about mesh 1. So let's go ahead and apply Kirchoff's voltage law to mesh 1. So I'm going to go ahead and walk clockwise in the direction of my current. Let's see what we get. I walk from minus to positive on my voltage source, so I get plus 12 volts. I have a voltage drop across resistor R1, another voltage drop across resistor R2. Okay, so there's our Kirchoff's voltage law equation. Now I need to rewrite that equation in terms of my mesh currents. So I need to get an expression for VR1 and VR2. Let's consider VR1 first. Notice VR1 is the voltage drop across resistor R1, and only current I1 is flowing through resistor R1. So by Ohm's law, I can say VR1 is equal to I1 times R1. I1 R1. Now try VR2. What would we get for the voltage drop across resistor R2? So notice you want to make sure you calculate the current through resistor R2 correctly. Here we can determine by Kirchoff's current law that plus I1 minus I2 minus IR2 equals 0, so IR2 is just I1 minus I2. So by that reasoning, the voltage drop across resistor R2 would be equal to resistor R2 times I1 minus I2. That's the resistance times the net current flowing through that resistor. So finally, if we substitute these voltages back into Kirchoff's voltage law, what do we get? We get our mesh equation for I1, which is plus 12 volts minus VR1, which is minus I1R1, minus VR2, which is R2 times I1 minus I2. So we get that whole thing. That is an example of a mesh equation. You can see that if we were to repeat this analysis for that second current, I2, you would see that we would end up with two equations and two unknowns, and we could solve for I1 and I2. All right, so once again, pay attention to those negative signs. Don't be afraid to draw pictures if you need in order to help when solving these questions. Okay, so let's go ahead and move on to our next example. And so here we are given another circuit, and we are asked to use mesh analysis to find the mesh currents. Let's walk through this example step by step. So our first step is to identify the meshes, and so in this case, we were already told to assume clockwise currents I1 and I2. Had we not been given those currents, we could have chosen to draw them in however we wanted. We'll keep them as I1 and I2 clockwise for now. So assigning a current to each mesh, once again, this was given to us already, so we will assume those clockwise currents. Let's move on to step 3. Well, remember, step 3 was to apply Kirchoff's voltage law to get equations in terms of the loop currents. So here we're talking equations in terms of I1 and I2. Well, wait a minute. Does this circuit look familiar? It turns out we already wrote these mesh equations. If you'd like, consider pausing the video and trying them again on your own. Let's go ahead and just remind everybody what these mesh equations are. So in this case, for our first loop, we end up getting plus 10 volts minus 5 I1. We have I1 going through that 5 ohm resistor, minus 9 volts, then minus 10 times, remember here we have I1 and I2 flowing through, so we have 10 times I1 minus I2 equals 0. Notice how I was able to come up with that mesh equation fairly quickly. Once you get comfortable with mesh analysis, it should be pretty quick and easy to write these mesh equations. So keep practicing until it gets comfortable. Similarly for loop I2, remember that we first had a voltage drop across the 10 ohm resistor. So in that case, the voltage will be minus, because it's a drop, we'll have 10 times, in this case, I2 is entering, I1 is leaving, so we have I2 minus I1. Then we gain 9 volts if we are walking around I2. We have our voltage drop across the 5 ohm resistor. Again, there's just only current I2 going through, so resistance is 5 ohms, current is I2. Voltage across a 5 ohm resistor must therefore be 5 times I2. Finally, minus 1 volt drop across the source, and another minus 5 I2 for our resistor. So notice here we end up with two equations, two unknowns. Our unknowns are I2 and I1. So once you've written the mesh equations, you've completed the hardest part of the question. Now all that's left is to solve for those currents. One thing to be careful of is signs, so make sure that you pay attention, especially for like this first resistor, you got a voltage drop, so be careful not to forget negative signs for voltage drops. And also when multiplying through, make sure you remember to distribute negative signs across all the different parts of your expression. So finally, last step is to solve our system of equations. And you'll remember we have these two equations. We can simplify and rearrange. And using our solver of choice, we can arrive at our final answer. So that wasn't too bad, right? The important thing here is to keep that consistent sign convention, draw pictures if you need, and make sure you apply Kirchoff's laws and Ohm's law correctly. I'd highly recommend you try going back through these examples on your own and verify that you understand mesh analysis. It's a very important tool that we're going to use all semester long. Finally, let's go ahead and talk about a few special cases of mesh analysis. Our first special case of mesh analysis comes up when we have a shared current source. What that means is if we have a current source which overlaps the current source overlaps two meshes, right? Or is shared by those two meshes. So here, both the mesh I1 and I3 contain that current source I. So here's what to do if that happens. If I have the current sources that are shared, I can create what's called a supermesh. And notice this supermesh is created around both shared meshes. So you define the supermesh to be the border of the meshes which share a current source. So notice in this case, we combine mesh I1 and I3, and we make this larger area here. We call that our supermesh. And then look what we can do. We can actually apply Kirchoff's voltage law to our supermesh. Remember, Kirchhoff's voltage law says the sum of rises and voltages across any closed loop must be zero, and the supermesh is still a closed loop. So here you can see what we did. We summed up the voltage rises and drops across each component, and we are left with a supermesh equation. And then we can apply Ohm's law to our Kirchhoff's voltage law, and notice we can recognize what currents are flowing through each component. So here we had I1 minus I2 flowing through R2, and then R4 only had current I3 going through it. So we're able to get what we call a supermesh equation. Supermesh equation is a mesh equation written for the supermesh. So supermeshes might sound a little scary, but please practice them and give them a try, and you'll see that actually it can make solving homework problems quite a bit easier. If you recognize that you have a supermesh in your problem, you can actually simplify things quite a bit. And once you have that super mesh equation, you follow the same steps we already know to complete the mesh analysis. Notice in this case the super mesh equation relates I1, I2, and I3. And you would just need to find two more equations relating I1, I2, I3. Then you would have three equations, three unknowns, and you could solve. One other special case of mesh analysis is when we have dependent sources. And in this case, the procedure is very similar to what we did with node analysis. General rule is if we have a circuit containing a dependent source, then we want to take the controlling current or voltage and express it as a function of the mesh currents. That's all we need to do. Once we express that current or voltage in terms of the mesh currents, we can proceed with mesh analysis as normal. Finally, before we do some last examples, let's briefly talk about when we would use node analysis versus mesh analysis. Remember that both node analysis and mesh analysis rely on Kirchoff's laws. So both methods are perfectly legal, and generally both methods could potentially be used to solve a circuit. Here's where things become a little bit more tricky. Sometimes one method is easier, or sometimes one method will not have enough known information. So sometimes there are situations when using node analysis or mesh analysis might be preferable. So remember that node analysis solves directly for voltage, mesh analysis solves directly for current. So node analysis typically handles circuits with current sources fairly easily. Mesh analysis with Kirchoff's voltage law prefers circuits with voltage sources. Depending on how many other voltage or current sources you have in your circuit, sometimes they can be easy to deal with. Other times it's more challenging. Here's the biggest rule though. This is what I think you should remember most. Generally, we want to solve as few equations as possible. So I recommend that you consider use the method which allows us to solve fewer equations. For example, if I had a circuit like this, where I have one node V1, but if I have two meshes, I1 and I2, notice that I would only need to write one mesh equation, or I'm sorry, only one node equation, but I would have to write two mesh equations for that same circuit. So if I had a circuit like this one here, I would probably want to use node analysis, because I wouldn't have to solve as many equations. So it becomes a little bit of an art to recognize what method might be best. Generally, there are multiple approaches that will work for solving different kinds of problems, but if you can take a look at what you know, try to recognize whether node analysis or mesh analysis will produce fewer required gates. So if you have a circuit that has very few nodes, node analysis might be a good approach. If your circuit has very few loops or meshes, mesh analysis might be easier. Also, keep an eye out for supernodes and supermeshes. Because remember, if you see a supernode or a supermesh, that can also provide a big hint about how to solve the problem. Okay, so with our remaining time, let's go ahead and do a couple more examples. Let's try this next one. Here we have a super mesh. And so here we are being asked to solve for the voltage VA. Everybody see the super mesh here? Notice we have a current source here, which is between, the current source is between two meshes. It's shared by both I1 and I2. So using a super mesh would be a good approach to solve this question. So let's go ahead and give this a try. So first we want to recognize that we need to use a super mesh because the two meshes, mesh I1 and I2, these share a current source. So we create the super mesh to be using the boundaries of the mesh I1 and I2 not shared by the source. So we define the super mesh as the boundaries of the mesh I1 and I2, which are not shared by the current source. So in this case, our super mesh becomes the perimeter of the circuit. Next, we can apply Kirchoff's voltage law to the super mesh. So remember, like before, we can just start walking around our circuit. And I'm going to go ahead and walk clockwise. And I'm going to start from the lower left. So what do I get? First, I have a voltage drop across my 250 ohm resistor. Then I keep walking. Next, I have a voltage drop across the 9 ohm or 9 volt source. I also have a voltage drop across that 100 ohm resistor. We know that voltage is also equal to VA, but for now, let's leave it in terms of just the 100 ohm resistor. So notice that's all I've got. I just have those three components, so the sum of voltage rises and drops must be 0. So I can rewrite in terms of the mesh currents. And so the voltage drop across my 250 ohm resistor. I only have I1 flowing through that part of my circuit. So in this case, I'm going to have negative 250 times I1 as voltage drop across 250. Next, I have my voltage across that 100 ohm resistor. So notice in this case, that branch of my circuit is only covered by current I2. So in this case, the voltage drop across my 100 ohm resistor, that's just going to be minus 100 I2. So I need another equation. Relating I1 and I2 so that we get two equations and two unknowns. Well, how else can we relate I1 and I2? Have any other ideas? What happens if we apply Kirchoff's current law to the bottom node? So let's take a look at what we have. We have a 0.02 amp source, and then we know that we have I2 going that way. We also have I1 going clockwise around the left loop. What happens if we apply Kirchhoff's current law here? Well, we know by Kirchhoff's current law, plus I2 plus 0.02 minus I1, that must be 0. Now we have two equations, two unknowns. So we can solve for I1 and I2. Then how do we find VA? Remember, our goal at the end of the day was to find VA. Well, we know VA is going to be equal to 100 I2. That's the voltage across our 100 ohm resistor. So once we know I2, we can plug I2 in to determine VA. So let's go ahead and do that. So if we go ahead and solve our equations, so if we solve our two equations for I1 and I2, again here you could use Wolfram alpha or solve by hand. Or you could use something like MATLAB or Cramer's rule. We determine in this case that I1 is equal to 0.02 amperes. I'm sorry, negative 0.02. And I2 is equal to negative 0.04 amps. Why are these negative? Well, they're negative because we assumed the currents were going clockwise. But it turns out they're actually going counterclockwise. Probably that 9-volt source produces a lot of current entering from the top, and it could very well be that because of that 9-volt source, the current actually flows the other way. So if you see a negative result, don't panic. That just means that the direction you assumed the current to flow was opposite of the actual direction. Okay, so now that we know I1 and I2, we can find VA, right? So we can go ahead and substitute in. We know that VA is going to be equal to 100 I2 And of course, that's 100 times negative 0.04. Again, this is 100 ohms, this is amps, so ohms times amps, that gives us negative 4 volts. So there you have it. Notice that once you write those mesh equations, these questions really aren't so bad. So make sure you understand the procedure to write these node and mesh equations and solve for unknowns. And feel free to reach out if you have any other questions on this. And there we go. Okay, finally, let's go ahead and end with one last practice question here, and this question might also be similar to something on a homework assignment. This question is asking, how could we solve this circuit using mesh analysis? Well, there's a couple things to note about this circuit. Do you see anything special? What is special about this circuit? Well, first, notice we have a shared current source. We also have a dependent source. So, in order to solve this circuit with mesh analysis, we're going to need to write a super mesh equation. I'm not sure which way my current is flowing, but we can write a super mesh equation. So in this case, we can write that the voltage drops across all of our resistors those must all sum to 0. Notice we can also define some mesh currents. So here, I don't know which way everything is flowing, but I do have this current source, so I'm going to assume my currents are flowing something like this. Again, I have no idea, but I'm just going to assume my mesh currents I1, I2, and I3. Notice I can now rewrite that mesh equation in terms of the mesh currents. So in this case, VR1, well, minus VR1, that just becomes R1 times IX, right? VR2, that's just going to be equal to R2 times I1 minus I3. VR3, notice we've got current I2 flowing that way, but I am walking in the other way. So notice in this case, VR3, this is actually going to have a positive sign due to my convention, so you got to be careful there. So here, VR3, I'm just going to say R3 times I2 for now, and then we be careful of the sign. Notice that we are going opposite the direction of the current there, so we need to treat that as a voltage gain rather than a voltage drop, the way we're walking. And then finally, voltage across R4, well, that's just R4 times, well, what do we have? We have I3 going this way, and we have I2 also going in the same direction. But we are walking the other way, so again, be careful, we're going to have to treat that, in this case, Since we're walking up, this will be treated as a voltage gain, and it will be, in this case, I3 plus I2. So we need to be careful of those current directions. Okay, so notice we got a mesh equation. And wait a minute, did you notice I wrote my voltage drop across resistor R1? I wrote that voltage drop across resistor R1 in terms of Ix, but how is Ix related to I1? Well, if you look closely, you can see that Ix must be equal to I1, because the only current flowing through resistor R1 is current I1. Another question to ask is, how do we keep that dependent source in the picture? Well, since Ix equals I1, we can relate the dependent source to be 4I1. So using that dependent source, we can also determine equations for the other currents. For example, consider this top node up here. I'll call it node 1. I have I1 or Ix entering. I have 4I1 leaving. And I also have I3 entering based on my convention. So notice in this case, I can write that plus I3 minus 4I1 plus I1 equals 0. So I can say that I3 minus 3I1 equals 0, or I3 equals 3I1. I can also do a similar approach at node 2 to get another equation relating I2, I3, and I1. So I can repeat Kirchoff's current law to get equations relating I1, I2, and I3. Once I have that, I can substitute into my supermesh equation. My goal is to get 3 equations and 3 unknowns, and then I can solve for my supermesh and solve for that current Ix. So I'd highly recommend you take a look at this problem and use it to help practice applying both Kirchhoff's current law and Kirchhoff's voltage law in order to reach a solution. And pay especially close attention to how you assign sign conventions. Notice that it's very helpful to draw pictures here to keep track of which way you assume currents are flowing, and also the direction you're walking. All right, so thanks everyone for joining the fun today. Hopefully now you're more comfortable with applying Kirchhoff's voltage law and Ohm's law to determine mesh equations. You should see that mesh analysis is a really powerful tool, and we will continue to use it. So make sure you start practicing applying mesh analysis to analyze circuits. And finally, keep an eye out for when you want to use node analysis versus mesh analysis. Remember, for circuits that contain very few nodes, node analysis might be easier. If your circuit contains very few meshes, then mesh analysis might be easier. Feel free to reach out if you have any further questions on this. Next time, we'll start covering some additional tools that are extremely helpful for simplifying circuits. Thanks, everyone, and we'll see you in the next video.